This is one of the most powerful jet engines in the world, and it actually runs at temperatures 250 degrees Celsius hotter than the melting point of the materials that make it up.
That's 1200 degrees.
So the question is, why doesn't a jet engine just melt into a puddle?
To keep a turbine blade whole and unaffected within an engine is like putting an ice cube inside your oven, turning up to max, leaving for work, coming back after an 8-hour shift and finding it still completely frozen in the oven. That's what we've got to try and do within that engine.
It sounds absurd.
Not only do the turbine blades sit in a stream of gas that's over 1500 degrees Celsius, they're also spinning at 12,500 RPM, with the tip of each blade slicing through the air at nearly 1900 kilometers per hour. Now, every blade wants to fly straight, but it's forced to spin in a circle, which means something has to be constantly pulling it inwards. That's the centripetal force. If you take a representative 300-gram high-pressure turbine blade and run it at that speed and radius, it has to be pulled inwards with a force equal to the weight of 20 metric tons. That's roughly the weight of 2 London double-decker buses tugging on each blade as it spins, all while they're glowing hot. To make matters worse, at these temperatures, oxygen wants to react with the metal of the blades itself. And on top of all that, the air rushing through the engine often carries dust, sand, and pollutants that can damage and erode the surfaces inside. And somehow, these blades have to survive this punishment for tens of thousands of flight hours without deforming, cracking, or failing. They really determine how efficient you can make the engine, because you can't make the engine so hot that the blades can't withstand that temperature. So they determine the maximum temperature of the combustion chamber and therefore the maximum efficiency you can realize with a jet engine. So what kind of metal could possibly survive these conditions? This is a mild steel. It's relatively strong and easy to form into complex shapes. It seems like a pretty good bet for a turbine blade, and at first, under this load and at these low temperatures, it holds up pretty well. We're essentially tugging on all the atoms within the metal. We're not breaking or forming any bonds, we're just making them flex a little, and that slightly changes the spacing between the atoms, and as a result, the metal gets slightly longer. This resulting change in size, specifically the per unit change in length, is what we call strain. Critically, at this stage, the material is behaving elastically. If we remove the load right now, the material just snaps back to its original size. In an engine, some elastic deformation like this will occur. It can't be too big or it'll cause problems. But what we really don't want is plastic deformation, if the shape changes permanently. And that's exactly what starts to happen as we keep increasing the temperature.